Hello, and a huge welcome to all the anesthesiologists and perioperative medicine specialists tuning in. If you're curious about artificial intelligence and how machine learning is set to change our field, well, you have come to exactly the right place.
You know that feeling, right? You look at the mountains of data we generate every single day in perioperative care, and you just know there are secrets hidden in there. You wonder, how can we unlock all of that potential? Well, this is for you. We are going to cut through the jargon and the buzzwords to give you a really clear, practical roadmap for using machine learning in your research. We're going to cover the whole journey, from that first little spark of an idea all the way to publishing a paper that can make a real impact. Okay, let's get into it.
So here's our game plan. We've laid this out to follow the actual path of a research project. First, we'll get a handle on what makes machine learning so powerful in the first place. Then, we'll open up the toolkit and look at the right models for the job. After that, it's all about how to build a paper that gets noticed, how to dodge the common mistakes that sink so many studies, how to use the latest reporting guidelines, and finally, the secret sauce for getting your work into a top-tier journal. So why is everyone so excited about machine learning and anesthesiology? Honestly, the promise here is just massive. It's all about building systems that can see patterns in data on a scale that's, well, it's just impossible for the human brain. Just imagine for a second, being able to tap into the collective experience, the wisdom from the outcomes of millions or even billions of past patients to help you care for the very next patient right in front of you. That's the dream, right? To make every single decision more personal, more precise, and more informed by everything we've ever learned. Okay, so what is machine learning, really? The key thing to understand is how different it is from regular programming. Normally we give a computer very specific rules. If this happens, then do that. Machine learning completely flips that script. Instead of feeding it rules, we feed it examples. We give it thousands, sometimes millions, of patient cases from our electronic health records, and from that data, the model learns the patterns all by itself. It finds these incredibly complex connections that we would never think to program by hand. So it's not about following our rules, it's about learning from experience to write its own rules. All right, let's get practical. It's time to open up the toolkit. This next part is all about the what. The actual models and algorithms that you're going to see in papers, and hopefully use in your own research. Getting a feel for how they're different is absolutely the first step to picking the right one for your study.
So you'll basically hear about two big families, classic machine learning and deep learning. Here's the difference in a nutshell. With classic ML, you, the expert clinician, have to tell the model what to look at. You handcraft the features, things like age, ASA status, creatinine. You're the guide. Deep learning is different. It's like a brilliant but brand new intern. You can just give it the raw data, like an entire arterial waveform, and it figures out on its own which little dips and peaks are important for the prediction. Now, that's incredibly powerful, but it's also why deep learning is so data hungry. It needs a ton of examples to learn from.
And check this out. This is a really fascinating trend. You can see how the field has shifted over time. Back in the day, neural networks were a big deal, but look at that surge in models like support vector machines and especially random forests over the last decade. So why? Well, it turns out that for the kind of data we work with most of the time, that structured table-based data from the EHR, these classic models often hit a real sweet spot. They're easier to work with, require less data, and can actually give you better results than a super complex deep learning model. Sometimes simpler is just smarter. So with all that in mind, think of this table as your starting playbook. It's not a set of absolute rules, but it is a proven, battle-tested strategy that reviewers love to see. Let's say you're predicting a binary outcome, a simple yes or no, like acute kidney injury. Your first move should be to build a classic logistic regression model. Everyone gets it, it's easy to interpret. Then you build a more advanced model, like a random forest or XGBoost, and you compare them. Does the fancy model actually do better? This two-step process, compare the classic to the advanced, is a sign of really rigorous, high-quality research. The same logic holds for mortality. Start with a Cox model, then maybe try a random survival forest. It's a fantastic approach. But here's where it gets really, really cool for us as anesthesiologists. What about all that unique, real-time data streaming from our monitors? I'm talking arterial waveforms, EEG. This is where those specialized deep learning models, like LSTMs, just blow everything else out of the water. See, they're built to understand sequences over time, so a simple model might see the current blood pressure. But an LSTM can see that and remember that the pulse pressure has been slowly narrowing over the last 5 minutes, a subtle pattern that screams impending hypotension. It learns from the history of the signal, and that is a total game changer. Okay, you've picked your tools, you've run the numbers, awesome.
Now comes what is, without a doubt, the most critical part, writing it all up. We need to build the blueprint for your paper, and we're going to put a huge spotlight on the methods section. Because for any ML paper, this is where the reviewers go first. It's where your study will either stand tall on a foundation of solid rock or just crumble. I want you to think of your methods section as telling the story of your data. Each of these steps is just a chapter in that story. Chapter 1, where did the data come from? Chapter 2, who was in the study? 3, what exactly were you trying to predict? 4, what clues did you use to predict it? 5, how did you clean up the data? And then the grand finale, how did you build and test your model? If you tell that story in that order clearly, you're giving the reader everything they need for transparency and reproducibility.
All right, we've seen what a good methods section looks like. Now let's talk about the dark side. Why do these papers get rejected? Seriously, knowing the common mistakes is the absolute best way to make sure you don't make them. It's time to get inside the mind of a journal reviewer and see the red flags they are trained to spot.
So before I just give you a list, I want you to pause for a second. What do you think it is? What is the #1 most fatal flaw that sends an otherwise good ML paper straight to the rejection pile? Take a guess. It's a concept that is at the very heart of this entire field.
And that's it. Right there. Overfitting. This is the cardinal sin of machine learning. Think of it like a student who memorizes every single answer on a practice test. They'll get 100% on that test for sure, but give them a real exam with slightly different questions, they'll fail miserably. That's overfitting. The model has memorized your data instead of actually learning the underlying patterns. And a model that can't generalize to new patients is clinically useless. Proving your model didn't overfit is probably your single most important job.
Now, overfitting is the big one, but it's got plenty of friends. Here are some other major landmines. Not having a clear clinical question to begin with. Data leakage. That's a sneaky one. It's like accidentally letting your model peek at the answers before the test. Being sloppy with missing data. Not validating your model on data from a different hospital. Having a model that's poorly calibrated, meaning it might be confident, but it's confidently wrong. And of course, just not explaining what you did clearly enough. At the end of the day, it all boils down to one thing: methodological rigor. It's just not optional. So, we've seen all the ways things can go wrong. How do you make sure you avoid them? Well, the great news is you don't have to figure it out on your own. There's a rulebook, a standardized framework that the research community has built, and it just got a major update for the age of AI. Which brings us to, for a long time, the tripod guideline was the gold standard. But as we've seen, machine learning brings all these new layers of complexity. So in 2024, they released Tripod AI. It takes all the great stuff from the original and adds new checkpoints just for machine learning. It asks you to detail how you processed your data, how you tuned all the little knobs and settings on your model to get the best performance, and it really pushes you to make your code available. From now on, if you're writing an ML paper, following the Tripod AI checklist is the new price of admission for getting published. Okay, we've reached the final leg of our journey. You've built a great model, you've dodged the pitfalls, you've followed the latest guidelines to write a killer methods section. So, how do you push your paper from being just good to being truly great? How do you get into those top-tier journals that can actually change the way people practice medicine?
Here's the secret. The top journals are tired of the horse race. They don't really care anymore if your fancy new model got an AUC of 0.85 and the old logistic regression got an 82. I mean, that's nice, but it's not the main event. What they want to know is, so what? They want to see clinical utility. How would a real doctor use this tool to help a real patient? Could it change a decision? Could it save resources? That question, the so what, is the new frontier.
And that leads me to my last point, and it's really a challenge for all of us. Let's start reframing our research questions. Instead of just asking, can we predict AKI? Let's ask something much more powerful. Let's ask, can we use our model to find the exact group of patients who will actually benefit from an intervention like goal-directed fluid therapy? And, just as importantly, find the low-risk patients who don't need it. You see the difference? We're moving from a passive prediction tool, a crystal ball, to an active instrument that helps guide therapy and personalize medicine. And that is the kind of research that has the power to truly change everything.